Hello everyone, welcome back. We are going to be doing the last section of chapter 3, which is hyperbolic functions. Definition of hyperbolic functions. So we are going to combine two exponential functions, namely the sum and difference, to write the sine hyperbolic x and cosine hyperbolic x. Sin hx is read as sine hyperbolic x. Cosine hx is read as cosine hyperbolic x. The sine hx is defined to be e to the x minus e to the negative x over 2. Cosine hyperbolic is e to the x plus e to the negative x over 2. Tan is sine hyperbolic over cosine hyperbolic x. Cosecant is its reciprocal of sine hyperbolic x. Secant hyperbolic x is the reciprocal of cosine hyperbolic x. Cotangent hyperbolic x is cosine hyperbolic x over sine hyperbolic x. Or you can also say 1 over tan hyperbolic x. If you look at the graphs of these, because they are combination of exponential functions, sum and difference for the sine hyperbolic and cosine hyperbolic, the sine hyperbolic looks like the red one. Then the cosine hyperbolic looks like the red one in the second picture. And then the tan hyperbolic looks like the red one in the third picture. Similar to the way trig functions are related to the circle, hyperbolic functions are related to hyperbolas. So if you look at the graphs, they look like hyperbolas. So a combination of hyperbolas. So just the way trig functions are related to circle, hyperbolic functions are related to hyperbolas. Just the way we did trig identities earlier, we have some hyperbolic identities, similar. Some of them are similar, some of them are minor modifications. The sine hyperbolic negative x is negative sine hyperbolic x. Now cosine hyperbolic square minus sine hyperbolic square x equal to 1. So note the change. In trigonometry, we know that cosine square x plus sine square x equal to 1. Pythagorean identity, you have added plus sign in between. Now you have a negative sign in between and it becomes 1. Then cosine h hyperbolic negative x is cosine h x because it's even function. So cosine hyperbolic is even function, which means if you graph, it will be symmetric about the y-axis, which is what we see here. If you look at the two branches of the red graph, they are mirror reflections about the y-axis. And here, sine hyperbolics is an odd function, which is clear from the first graph that you see in the table. 1 minus tan hyperbolic is secant hyperbolic square x. So earlier in trig 1, you have 1 plus tan square. So in trig, you have 1 plus tan square equal to secant square x. So in hyperbolic, you have 1 minus. Then sine hyperbolic x plus y, it is kind of sine hyperbolic sum, where you have a sum here, x plus y. So it is similar to the trig sine sum formula. Sine hyperbolic x, cosine hyperbolic y, plus cosine hyperbolic x, sine hyperbolic y. Cosine h x plus y, cosine hyperbolic x, cosine hyperbolic y plus sine hyperbolic x sine hyperbolic y. So in the trigonometric function, you have a minus in between. Now we have a plus in between. We'll try to show some identities here. Prove cosine hyperbolic square minus sine hyperbolic square equal to 1. So let's take, anytime you prove an identity, you have to start from one side and arrive at the other side. Let's start with the left side. Cosine hyperbolic square x minus sine hyperbolic square x, which is cosine hyperbolic x, the whole square, minus sine hyperbolic x, the whole square. By definition of hyperbolic function that we have defined earlier in this table, so I'm going to substitute for cosine hyperbolic. I'm going to substitute for sine hyperbolic. So it will be 1 over 4. Then you have e to the x plus e to the negative x, the whole square, minus 1 over 4, e to the x minus e to the negative x, the whole square. That is 1/4. If we expand this, it is e to the x times e to the x. We're going to use the formula a plus b, the whole square, is a square plus 2 times ab plus b square. So it's e to the x, the whole square, that is e to the 2x. Then you have twice e to the x, e to the negative x, plus e to the negative 2x, minus 1/4, e to the 2x, minus 2 e to the x, e to the negative x, plus e to the negative 2x. In these two, you notice 1/4 is common. So you can take that out. Then you write e to the 2x plus 2, because e to the x times e to the negative x is e to the 0, which is 1, and plus e to the negative 2x. Then you distribute the minus sign, e to the 2x. Again, this is e to the 0, which is 1. Minus and minus makes it positive. Then you have a minus e to the negative 2x. So you have some of them getting cancelled here. That is just 4 inside. There is a 4 outside. There is a 4 inside, which will add up to 1, which is now the right-hand side. So we have proved cosine hyperbolic square x minus sine hyperbolic square x equal to 1. For this part, part B, 1 minus tan hyperbolic square x. We're going to prove that to be equal to secant hyperbolic square x. So to do that, we can actually take the identity that we have proved. This is to be proved. So let's start with the identity that we proved from part A, which is similar to Pythagorean identity, except the sign. So cosine hyperbolic square x minus sine hyperbolic square x equal to 1. You will divide everything by cosine hyperbolic square. So this will be just 1. This will be tan hyperbolic square, because sine hyperbolic over cosine hyperbolic equal to tan hyperbolic. You have a square of that. This will be reciprocal of cosine hyperbolic square, which will be nothing but secant hyperbolic square. So this is the left-hand side of the identity that we have to show. This is the right-hand side of the identity. Thus, the identity is proved. Then derivatives of hyperbolic functions. So derivative of sine hyperbolic is cosine hyperbolic, which we have, which is exactly similar to the derivative of sine trigonometric function. Derivative of cosine hyperbolic is sine hyperbolic. Note the change here, because derivative of cosine x, the trig function, is actually negative sine x. Derivative of tan is secant hyperbolic square x, which doesn't change. Derivative of cosecant hyperbolic is negative cosecant hyperbolic, then cotangent hyperbolic. It's exactly similar to trig. Derivative of secant hyperbolic is negative secant hyperbolic, tan hyperbolic. Note the change here. Derivative of secant x is just secant x tan x for trig functions. Derivative of cotangent hyperbolic is negative cosecant hyperbolic square x. So it's better to memorize these formulas. Let's use these formulas to do the derivative of cosine hyperbolic root of x. So if you recap the chain rule that we did, so if you have, let's say, cosine of some function, okay, then you want to differentiate that. What do we do? Which is negative sine box times derivative of the box. So this one is the outer derivative, and this one is the inner derivative. So that is the chain rule that we will be applying here also for hyperbolic though. So the question is d by dx of cosine hyperbolic root of x. So consider root of x as your box. So it is outer derivative, which is derivative of cosine hyperbolic, which is just sine hyperbolic. Keep the inside as is. Then derivative of the inside. Derivative of the box. So it is sine hyperbolic radical x times 1 over 2 radical x. A better way to write this would be 1 over 2 radical x in front, followed by sine hyperbolic root x. The idea is that we don't want to confuse this 1 over 2 radical x along with this argument of sine hyperbolic. That is derivative of cosine hyperbolic radical x is 1 over 2 radical x sine hyperbolic radical x. All right. Now let's try some of the additional suggested problems from the exercise. It's better to try as many as you can. Let me show some of them over here. So prove the identity cosine hyperbolic negative x equal to cosine hyperbolic x. We are proving an identity here. So this is number 12. Prove the identity. Cosine hyperbolic negative x equal to cosine hyperbolic x. We'll start off with the left-hand side. Cosine hyperbolic negative x. So we know that cosine hyperbolic from the table is defined to be e to the x plus e to the negative x by 2. So if it is x, the exponents are x and negative x. So we have cosine hyperbolic x, which is e to the x plus e to the negative x, all divided by 2. So we are going to replace, because we have negative x in here, we are going to replace all the x with the negative x in the formula. So it is e to the negative x plus e to the negative of negative x So this x here gets replaced by negative x. So it will be e to the negative, this divided by 2, of course, e to the negative x plus e to the positive x divided by 2. If you switch the terms, it's e to the x plus e to the negative x by 2. What is this one equal to? Cosine hyperbolic x. So cosine hyperbolic negative x equal to cosine hyperbolic x, which is proved. So incidentally, it proves that cosine hyperbolic is an even function. What is an even function? If f of negative x is same as f of x, then f is said to be even. That's what's happening here. By changing x to negative x, the equation, the function is unchanged. So it is an even function. Now let's try some derivative problems. Problems based on the derivative. Let's try practice test number 36. So it's f of x equal to e to the x cosine hyperbolic x. The question is find the derivative. That means we are finding f prime x. So we are going to find out f prime x. So for that, what do we do? Because it's product of two functions, treat one of them as u, the other one as v. So it's product of two. So let's say u equal to e to the x. So its derivative is e to the x. And v equal to cosine hyperbolic. What is its derivative? Sine hyperbolic. You can refer the table also. Right? So f prime x, which is the product row for derivatives, is u v prime plus v u prime. U is e to the x. V prime is sine hyperbolic plus v, which is cosine hyperbolic, u prime, that is e to the x. In these two, you notice e to the x is a common factor. So e to the x times sine hyperbolic plus cosine hyperbolic. That is the answer to the problem. We'll take a couple more derivative problems. This problem is already done in chapter videos. So let's try something different. Number 41, tan h square root of x. Practice test 41. which is find the derivative of f of x equal to tan h square root of x. The question is the derivative. So you have to recap again chain rule. So f of x can be written as tan h of a box, right? You have a box. So how do you do the derivative? F prime would be secant hyperbolic box times derivative of the box, secant square. Derivative of tan is secant hyperbolic square. So that's what we are going to do here. So that is by chain rule. So it is secant hyperbolic square of that radical x times derivative of radical x. The derivative of radical x is 1 over 2 square root of x. So secant hyperbolic square root of x times 1 over 2 radical x. So we don't want to confuse this 1 over 2 radical x with the argument of secant hyperbolic square. That's the reason we wrote that in front of the expression. We can try one more of the derivative, which could be either ln or 46. Let's try 46 here. So find the derivative of f of t, which is equal to 1 plus sine hyperbolic t over 1 minus sine hyperbolic t. So this is of the form u over v. You want to find out the derivative. So apply quotient rule. So f prime t would be v u prime minus u v prime divided by v square. What is u? The numerator, 1 plus sine hyperbolic t. What is v? The denominator, 1 minus sine hyperbolic t. What is u prime? Derivative of 1, 0, derivative of sine hyperbolic is cosine hyperbolic. Then derivative of 1 is 0, derivative of sine hyperbolic is cosine hyperbolic. So now plug in these values here. V, which is 1 minus sine hyperbolic, times u prime, is cosine hyperbolic, minus u, which is 1 plus sine hyperbolic, v prime, that is negative cosine hyperbolic, divided by v square, is 1 minus sine hyperbolic, the whole square. Now distribute the numerator, cosine hyperbolic minus sine hyperbolic times cosine hyperbolic. Minus and minus, that will become plus cosine hyperbolic. Then you have minus and minus, that will be a plus sine hyperbolic, cosine hyperbolic. So these, and then of course the denominator remains the same. There is no change on that one. You notice on the numerator, these two terms are equal and opposite. So you have two cosine hyperbolic h function on top. You add them, they are similar kinds. In this case, f prime t is 2 cosine hyperbolic t over 1 minus sine hyperbolic t, the whole square. So in this concept video, We have done problem number 12. We have done problem number 36, problem number 46, and problem number 41. We have tried all these. And you also have some more in the chapter videos. So check them out. So that finishes chapter 3. So follow me for chapter 4.